So natural growth and decay. Let's come up with the model for it. So let's say that your differential equation dx dt equals kx. In other words, your rate of change of x is proportional to x. So the rate of change of x is proportional to x. And it really should be the rate of change of x with respect to time, right? Because it's with respect to t. And this happens with population growth, right? The bigger your population, the larger it can grow because there's more people who can make babies and stuff, right? Now, if you look at this, this is actually separable. Let's get all the x's on one side. You get dx over x, and then multiply by dt. Does everyone see how I've managed to separate? So what gets confusing sometimes is what your variables are, right? You have dx and dt, so your variables are x and t. You integrate. What's the antiderivative of dx over x? Natural log absolute value x, and then you get kt plus c. Okay, what can you now do? Just like we did in that first example, raise everything to the power of e. E to the natural log of the absolute value of x is the absolute value of x. And you get e to the kt plus c. Now again, what can you now do with your e to the kt plus c? So yeah, times a constant. The e to the c is just a. So you get a e to the kt. And then because the exponential is always positive, you just get x. So what's your general solution? The value of x, depending upon time, is equal to a to the kt. This is where exponential growth comes from. Exponential growth happens when the rate of change of your value is proportional to the value itself. That's what it means. That's what it means. Oh shoot. That's what it means to have exponential growth. Sorry, I was like dying there. I was like, wait, I'm not able to say this right. Okay, so where does this even come from? It comes from being able to separate the variables, right? Does everyone see how the solution like naturally arises from the fact that they are separable, basically? Right? So like what happens a lot of the time is that a lot of differential equations which are separable end up having an exponential as a solution. Why? Because you get that dx over x, right? And when you take the antiderivative, you get the natural log of x. And then how are you going to solve for it? By raising e to the power, right? So that's why you always end up with these exponentials, basically. So hopefully that makes sense intuitively now as to why you're going to get exponentials as the solutions to a lot of these separable equations. Another one that happens that we run across a lot is with what's it called? We talked about it, Newton's cooling, the cooling law. A very similar thing happens. Okay, so for instance, remember we said that like the way the cooling law works is the derivative of temperature with respect to time is proportional to the difference between the outside temperature and the temperature of the object. Okay, so like a very common problem of this would be like, let's say that at time t equals 0, 5 p.m. Wait, where is it? We are roasting a roast beef. The temperature of the oven is 375 degrees Fahrenheit. At when we put the roast in, it is 50 degrees Fahrenheit, and 75 minutes later it is 125 degrees. Find the particular solution which models the temperature of the roast. Okay, so we know that this is the model that we're going to have to use for this. Oh, it's hiding the problem, my bad. Is that better? Okay, cool. Sorry about that. So we set stuff up. We know that the derivative of temperature with respect to time is equal to K times the outside temperature, the oven is 375, minus T, which is the temperature. So that has us set up. Okay, so let's solve the differential equation. We want everything with T on the left, so we're going to get dt over 375 minus T equals K dt. And we're going to integrate. So all I did was just move everything around. Okay, we can do U substitution on the right. Does it make sense? You would set your U equal to 375 minus T. And then what would your du be? It would be minus dt. Right, so that ends up being the antiderivative of minus du over u. So you get minus natural log absolute value 375 minus t equals kt plus c. Are there any questions about that u substitution that I made? Do you remember doing that from 101B? That's why we spent a bunch of time on all those u substitutions. Okay, cool. Okay, now what are we going to have to do? I guess we should also move this minus over. Multiply both sides by minus. That way we don't have to worry about that. So what are we going to get? 375 minus t equals e to the minus kt minus c. Okay, now that e to the minus c, we'll just call that a. So we get a e to the minus kt. And then 375 minus t is equal to that. Okay, and then what you could do is solve for t. So you would get t equals 375 minus a e to the minus kt. Now notice that you have two constants, the a and the k, and that's actually why you need the two initial conditions of t of 0 equals 50. It went in at 50, and t of 75 equals 125, right? Because if you plug in t of 0, then this part will disappear, right? And you'll be able to solve for what a is. And then once you've got a, then you can plug in this one over here, and you can solve for k.